Over the last century or more, organic synthesis has offered numerous benefits to our society, including safer and more effective medicines, better crop protection, enhanced energy production and storage, and new materials for consumer products. Unfortunately, considerations for the environment were often an afterthought, and by the middle of the 20th century, the adverse effects of the chemical industry on the environment were apparent. Acid rain was polluting our waters and destroying our forests, holes had developed in our ozone layer, and compounds linked to cancer were in common use. The field of green chemistry evolved in the 1990s to begin tackling these issues. Now, green industry is a set of guiding principles established to help prevent various forms of pollution and other hazards. Rather than focusing on the proper handling of materials after a synthesis has been carried out, the goal of green chemistry is to avoid the production and accumulation of hazardous materials in the first place. Green chemistry drives the innovation of new chemical reactions, new techniques, and new technologies, which are generally known as green alternatives. There are 12 distinct principles of green chemistry, which I encourage you to look up on the American Chemical Society's website. I've shown you the link here. A thorough discussion of all 12 principles is really beyond the scope of this course. And so what we're going to focus on are some overarching ideas and how to apply to a handful of reactions encountered in the previous chapters. One of the things that I focus on in our laboratories, green chemistry, I'm really passionate about not generating a lot of waste. A really good example of this is that the distillation reaction that you use, a traditional distillation, used two hydrocarbons, neither of which could, both of which were pretty hazardous. And so a green alternative is using water and ethanol, which are much less hazardous. We use some green alternatives in general chemistry lab, notably the reaction where you make candles. That was changed to be a green alternative. So you can you make candles and use the products, so we don't dispose of those. So that's one of the things that, at least here at Cumberland, we're very, very passionate about. So one of the ways that you can kind of utilize green chemistry is by using toxic reagents. So even when proper safety precautions are taken, there's still some risk that the compounds used in a synthesis will be released into the environment, or the people involved in the synthesis will be exposed to those compounds. So green chemistry emphasizes that it's better to use less toxic, or non-toxic is really the goal, reagents and solvents whenever possible to minimize those adverse effects. A really good example of this is this reaction using molecular bromine. It's a rather hazardous compound. And so to avoid the direct handling of bromine, we can employ other reactions like the ones shown here, right? Where we're going to use aqueous solutions of hydrogen bromide and hydrogen peroxide. Now, hydrogen bromide and or hydrobromic acid and hydrogen peroxide are also hazardous, but they're generally considered to be safer than bromine gas. So this is considered to be a green alternative. Solvents are a huge concern when it comes to green chemistry because they're typically used in really large amounts in chemical reactions. And so we first encountered choices of solvents in Chapter 9, where we learn that protic solvents like water and ethanol favor SN1 and E1 reactions, and aprotic solvents like DMF or NN-dimethylformamide favor SN2 and E2 reactions. So an SN2, so for example, if an SN2 reaction is required for synthesis, you might first consider using an aprotic solvent. However, in this case, an SN2 reaction would take place in either water or DMF because the azide anion is a strong nucleophile. So a greener choice would be using water. This always gives me such heebie-jeebies because I used DMF and DMSO as solvents when I did my undergraduate research and did not wear gloves, and quite a bit got on my skin, which was unfortunate, and it's a liver toxin, so it always really freaks me out. So also wear gloves. We're all going to be safe in the lab. Okay. Sometimes the synthesis can be greens in terms of the byproducts and other waste that it produces, but should be avoided if it poses a high risk for accidents, including fires and explosions. For For example, when we convert this carboxylic acid into a methyl ester, we discussed this in section 10, right? This guy here, CH2N2, is explosive. So even though it's a really favorable reaction, this guy will explode. So you have to be really careful of this. And so if you have a safer alternative to use, you should use it. And so we're going to learn in chapter 23 that this same reaction here can be accomplished using methanol and a catalytic amount of acid, so just a little bit of acid. And we'll do the exact same thing. And these are much, much safer alternatives than things that can explode. So for any reagents used in synthesis, there's a risk of release into the environment, as well as human exposure. The same is true for any byproducts or other accumulated waste. So green chemistry places value on incorporating as much of the starting material into the desired products as possible, right? And so one way to do this is to maximize the percent yield. Even though if a reaction proceeds at 100% yield, it can still be quite wasteful. For example, if we look here, the alcohol and sodium bromide byproducts are unusable in the synthesis and would be discarded. And these byproducts represent a significant amount of material that would go to waste. By contrast, if we look at the epoxide ring opening mechanism here, in this case, all of the material that reacts ends up being in the desired product. If the reaction were to proceed at 100% yield, then none of the starting materials would go to waste, and you wouldn't have any byproducts that were unusable. So this reaction is just inherently more efficient than this reaction here. This type of efficiency is called percent atom economy, and it's calculated this way by taking the mass of the atoms in the desired product over the mass of the atoms in all the reagents. And when the numerator and denominator are the same, as for the case of the epoxide opening reaction here, the atom economy is 100%. On the other hand, if they're unusable byproducts in the synthesis, the atom economy falls below 100%, and that's the case for this elimination reaction here. So we are now going to calculate the percent atom economy of this elimination reaction right here. So here's our problem. It says compute the percent atom economy for the elimination reaction shown here in 1158. And so when we do this, we've got some questions here. Whenever I do math problems, I always like to go ahead, if I know what I'm working on, and write percent atom, use the equation, economy equals the mass of atoms in the product, in the desired product, over the mass of atoms in all reagents, and then times 100, okay? And so the first question you really need to ask yourself is, what is the desired product and what's the mass of its atoms? Well, the desired product here is the alkyne, right, which is shown right here. That you didn't even have to figure out, it just says desired product, right? And so when we look at that alkyne, the formula there is C8H6. So when you look at all the carbons and you add up all the hydrogens, you should get C8H6. Now, the total mass of those atoms are 102.14 U. Then we look at the mass of all the reactant atoms. So the reactant atoms are here. The molecular formula of the dibromide here is C8H8Br2. And so that's got a mass of 263.96 U. And then we've got two NaOCCH3s. So each one of those is 113.13 U, but there are two of them, so times 2 equals 226.26 U. So you have to add those together. So we're going to take 226.26 U and add it together with 263.96 U. And that gives us 490.22 U. Okay, and so how do we calculate the percent atom economy from these values? Well, you can see here we're going to take the mass of atoms in the desired product, which is 102.14 U, and we're going to divide it by 490.22 U and multiply it by 100. And when we do that, we get 20.84%. And so when you compare this to the previous problem, you can see that the reaction with the 100% yield or 100% atom economy is a greener choice because we're not wasting, or these byproducts aren't necessarily going to waste. We're not taking a lot to waste there. Now, a number of factors contribute to the cost of synthesis as well. Things like the purchase price of the starting materials, the time the synthesis takes, the cost associated with the disposal of waste that are generated in each synthetic step. And so for multi-step syntheses, these costs typically decrease significantly as the percent yield of the target increases because less starting material is used and less time is spent in the laboratory and less waste is generated. So we always seek to maximize the percent yield of a synthesis. And so we apply this by kind of using two specific rules. The number of steps in a synthesis scheme should be minimized, and each step in the synthesis should proceed with the highest possible yield. These rules are essentially an outcome of how percent yield is computed for a linear synthesis. And that's just a synthesis that's composed of sequential steps. And so for a linear synthesis, the overall product yield is equal to the product of the yields of the individual steps. So let's look at how to do this math. So consider two syntheses, one with 3 synthetic steps and a second with 6 synthetic steps. So if both these syntheses produce 80% yield, what would the overall yield be? Well, for a 3-step synthesis, and each one is 80%, you take 0.8 times 0.80 times 0.80, which would also be the same as saying 0.80 cubed, and that equals 0.51. So that means the overall yield equals 51%. But if you were to have a 6-step synthesis, that would be 0.80 raised to the 6th, that would be 0.26. So now you only have a 26% yield. So the synthesis with the fewest number of steps has the greater overall yield. So a lot of times I like to say, you need to be a lazy scientist, right? The fewest number of steps is what you really want, the maximum yield. This, I feel like, a really interesting table because it just illustrates how dramatic the overall yield of a synthesis can change with the number of steps and yield in each step. So the published syntheses of natural products commonly consist of about 15 to 30 steps with overall yields of less than 5%. And so you can see here, if you've got 20 steps and the yield per step is 70%, your overall yield, once it's all said and done, is just 0.08%. So if you think about Taxol at the beginning of the chapter, which was just such a triumph as its time, it was such a big deal. We could synthesize this molecule. It was great. Its overall yield, when it was all said and done, was just 2%. So the amount of starting material that they had to start with was just huge to finally get enough product, right? And so that's why if you go and join an organic chemistry lab, your PhD project may be doing a big synthesis like that, but trying to reduce the steps so that you can get a better overall yield because it's cheaper, it's less expensive. Now, one of the really common techniques is a convergent synthesis. So far we've only talked about linear syntheses. In a convergent synthesis, portions of the target molecule are synthesized separately and are assembled together at a later stage. In general, the yield of a multi-step synthesis is higher if a target can be produced from a convergent synthesis rather than a linear one, right? And so let's look at this next figure, okay? So when we look at this, both here and here depict an overly simplified synthesis to a target, okay? So there's our target. And in figure 11 this is 11.6a, so this is the top part. We have 2 carbons added each time, and 7 steps are required. And if we assume an 80% yield for this, then the overall yield would be 0.80 raised to the 7th power, which equals 0.21 or 21%. Okay. Now, 11b shows a convergent synthesis, right? Where you've got 2 8-carbon pieces that are connected together in the final step, with those pieces being constructed separately from the 2-carbon source. Okay. So reaching the final target still requires 7 steps, but the longest branch of the synthesis is only 4 steps. So when we think about this, the overall yield here, right, is really only 0.80 raised to the 4th, which equals 41%. And so that's roughly twice the yield from the linear synthesis. So convergent syntheses tend to be just more efficient. So for us, this ends chapter 11. It also ends organic chemistry 1. We will pick up in organic chemistry 2, looking at more reaction syntheses.